Okay, welcome to 3.9, day 2. Okay, so just recall that our derivative of e to the x is e to the x, or you could go with the chain rule on that and say the derivative of e to the something is e to the something times the something prime, or du dx, you could say, if you want our notation consistent. Right? And then we also saw this with other bases. So d dx of a to the x, which is just a to the x, times ln a, or chain rule d dx a to the u equals that same a to the u times ln of a times u prime, which is, by definition, the derivative of u with respect to x. Okay, so let's go on and look at our next topic. If we're going to talk about e to the x, then it stands to reason that we need to discuss ln of x. ln of x is, remember, the inverse function for e to the x. Since e to the x is a differentiable continuous function, ln of x is also, and it should have a derivative. Okay, so the problem is it's a little bit hard to work out if you're trying to use the difference quotient. So we're not going to use the difference quotient. We're actually going to kind of cheat on this. We're going to start out with this expression, and we're going to do an inverse on it. So we'll invert the equation. E to the y equals x. This is the inverse form. I take the derivative now. Now find dy dx. Okay, so if we find dy dx, find d dx on both sides, the derivative of e to the something is just e to the something times the something prime. Or you can just write y prime. The derivative of x with respect to itself is just 1. So we end up with dy dx equals 1 over e to the y. Okay, so let's just summarize our result. So we just learned then that the derivative of ln x is simply 1 over x. Now the chain rule for that would be d dx of ln u is just 1 over u prime, or you could write du dx. Oops. So 1 over u du dx, like that. Another nice way to write this is that the derivative of ln u is simply u prime over u. So that's a nice way to do it. Okay, let's look at an example of a problem that might involve the chain rule. So this problem says find dy dx if y equals natural log of, and then there's a function inside. So the first thing you want to do is identify the function u, because the derivative is supposed to just simply be y equals u prime over u. Excuse me, y prime equals u prime over u. So the u for this problem is 10 over x squared plus 5x minus 1, which I'm going to write as 10 times x squared plus 5x minus 1 to the minus 1. U prime, if we're using the chain rule, which is easier than the quotient rule, can be found by simply bringing down the negative 1, changing it to a negative 2, and following the chain. So it's going to end up being negative 10 x squared plus 5x minus 1 to the minus 2 times the derivative of the inside, 2x plus 5. And the cool thing about our answer is it's just the ratio of the two. So the u prime goes on top, and the u on the bottom. And I've put them both in the exponential notation. Okay, and then we can simplify it. Those cancel out. It leaves us with a negative 2x plus 5 on top, and an x squared plus 5x minus 1 on the bottom. So what happened to the other x squared plus 5x minus 1 to the negative 2? I'll let you think about why these two end up being just this on the bottom. Okay, so maybe you can pause it and tackle that. Okay, so there it is, our first example of one done with a chain rule. It's not really very difficult to do. Just need the u prime and the u and make a ratio. Very, very nice. Okay, our next problem says a line with slope m passes through the origin and is tangent to the graph of y equals natural log of x. What is the value of m? Okay, so it seems like this problem doesn't really give us enough information, but if we have a chance to sketch natural log of x, I think we'll realize that it's very specific, actually. Okay, so I'm just going to remind you real quick of how to sketch a graph that you don't know. If you don't know the natural log of x graph, you might know its inverse graph, e to the x. So e to the x looks something like that. So just a quick reflection over the y equals x line gives us something like this. This would be the natural log of x. Okay, so I'm actually going to bring in some graph paper and do it right, but I just wanted to show you that. I'm going to erase this and draw a little bit better sketch. Okay, so here I have it. I'm going to be graphing e to the x. I'm sorry, the natural log of x. Natural log of x actually passes through 1, 0. And it actually passes through e comma 1. E is between 2 and 3. A little closer to 3, actually. So it looks something like this. Okay, so they're saying that there's this line that passes through the origin and is tangent to this. So that is a very specific line, actually. It'd be something like this. That is very specific. There's only one line like it that touches the origin and the curve in a tangent fashion. Okay, so what is the slope of that line is the question. Okay, alright, let's take a look at the problem from two perspectives. Alright, the first perspective is that a slope of a line can be calculated by using 2 points on the line. Okay, so we can say that slope is simply y2 minus y1 over x2 minus x1, and the Algebra 1 student knows that. But we've also learned that if we're dealing with a tangent line, that is, that it's also f prime of a. Okay, so this actually is the information that we need to solve the problem. Okay, so what are my x1, my y1? That would be the origin, point 0, 0. Okay, what is my x2 and my y2? Well, that's the point on the curve. Now, I don't want to put x2, y2. I'm going to put something like a, comma, ln a. Because this point is on the black natural log graph. So it should obey the rule where the x value and the y value are related according to the function. So this is basically a and f of a. Okay, so I've got my x1, I've got my y1, I've got my x2, I've got my y2. Now all I need is my f prime of a. Well, the function is natural log. So f prime is just 1 over x. Okay, so f prime of a is also known, it's just 1 over a. Okay, so let's put this all together. Okay, if I plug in the y2 minus the y1 over the x2 minus the x1 and set this equal to the derivative at a, I end up with the following statement. ln of a over a equals 1 over a. Okay, these cancel out. And I'm left with the statement ln of a equals 1. And if you remember what ln means, ln literally means log base e. This basically means a equals e to the first. Or you could just say just a equals e. Okay, so how are we supposed to express our answer? Well, we need to write m. Okay, so the final answer is m equals 1 over e. And I'm getting that from right here. Okay, if you remember our discussion about e to the x, we also switched gears and started talking about a to the x. Remember? We need to do the same thing with logarithms. We've talked about base e, that's the natural log. We need to also talk about other bases, so we'll call those base a. Alright, so we'll start by inverting the statement as before. Okay, so that starts out by writing it as, instead of log base a of x, writing it as a to the y equals x, which we can then differentiate implicitly. So it would look like this. The left side is a to the y ln a times y prime. I'll just use the Leibniz notation. So that's the chain rule for the left side. And this is just 1. And then if we divide, we get dy dx equals 1 over a to the y ln a, or we can summarize that by saying d dx of log base a of x turned out to equal this. The a to the y part can be replaced with x. So we'll put that in. It's 1 over x ln a. Okay, and the chain rule, for that would be d dx of log base a of u is 1 over u ln a times du dx. Or you could say the derivative of log base a of u is u prime over u. Boy, that looks familiar. That looks like the one for ln. There's just an extra ln a on the bottom. You're welcome to just use the formula here at the end. Okay, so our example that involves the chain rule would be this one. So you can identify your u here. This is your u. So you can identify the u as root x and then immediately find the du to get yourself all set up. Okay, so if u is root x, then du dx, or just u prime, we'll just use the prime notation. U prime is 1/2 times x to the minus 1/2, or just 1 over 2 root x. Okay, so this problem is a y equals log base 5 of u problem. So the derivative will simply be u prime over u ln 5. Isn't that nice? Very nice. Okay, let's plug it in. U prime is 1 over 2 root x, and u ln 5 is root x ln 5. This ends up being 1 over 2x ln 5. Final answer. Okay, let's do another one. This time the u is just a little bit more complicated. So here's our u. Okay, but it's a log base 3 of u problem. So the derivative, if this really is a log base 3 of u problem, should simply be u prime, oops, sorry about the mess there, should be u prime over u ln 3. Okay, the u for this problem is 1 plus x ln 3. What is the derivative for that? Okay, now don't be fooled by this. The derivative of 1 is 0, we know that. This is just a number times x. This is not a natural log function taking the derivative. This is a linear function. It's like 0.7x or whatever it is. Actually, it's closer to 1 point something x. So the answer is just ln 3. Just in the same way that the derivative of 5x is 5. The derivative of ln 3x is ln 3. Okay? Alright, so our u prime is simply ln 3. Alright, let's go over here and plug it in. U prime goes on top, and on the bottom, our u ln 3. This is kind of a fun one. This actually canceled out. And we ended up with y prime equals 1 over 1 plus x ln 3. Now, if you're not comfortable with your answers, you're welcome to go to Wolfram Alpha and get the solution from the website. Their website, you can actually type in the question. You'll have to learn to type it a little bit, or ask me and I can show you, but you can always check your answers, and these are in the back of the book for the homework problems anyway. Okay, now this is our last example, and this is where things get really fun. We're going to be able to handle just about anything after this stuff. So this is the end of the chapter. This is kind of our last example together. This is an example of a problem that appears at first to be of a type x to the something. So your first thought might be to bring down the tan. Okay. Take away 1 or something like that. Okay, that's a good thought. It, at the same time, though, looks like an exponential because it has x up in the exponent. So what in the world is this all about? Okay, so one of the nice things about learning the logarithmic differentiation for today's video is it allows us to do something where we take the natural log of both sides and rewrite this as a product rule problem with implicit differentiation. Let me show you what I mean. So if we put an ln on both sides of this problem, the tan x can fall to the front. Now this is not taking a derivative or anything, this is just one of the rules of logarithms. So this brings down the tan x. The problem now looks like this. Okay, let's find the derivative of both sides. So d dx ln y equals d dx tan x ln x, and this is a product rule. Okay, this side is 1 over y prime, and this side is secant squared x ln x plus 1 over x tan x. Okay, so let's multiply both sides by y, and we get our answer. This is the correct answer. Right, and y is, if you remember, x to the tan x. Okay, so here's the final answer. Y prime is equal to, and then it's x to the tan x times secant squared x ln x plus tan x over x. And that I recommend you use with this method where I returned the by using a natural log on both sides, which is an old pre-calc trick. We were able to turn this into a problem that was all on one line, no exponency, and that's the end of the chapter.